Hello, everyone, and welcome to today's webinar. We're going to be looking at AC mitigation models in Canada, some of the common challenges, and in turn, the solutions to those challenges. I'm Nick Rendell with Technical Toolboxes, and today we have two very special guests, Ryan Hewes on the Rysco Corrosion Services side, and Joe Pikas from Technical Toolboxes. Moving on to the agenda, we've got a couple pretty packed agenda for you today. So we're going to start with Ryan from Rysco, look at, again, from Canada, what are the biggest challenges in AC interference? How do we mitigate those challenges? And then, really look at some live examples, case studies, that sort of thing. And then moving on, we'll kind of look at the AC mitigation power tool and, how at Technical Toolboxes we kind of mitigate some of these things as well. One more housekeeping item real quick. Just want to let you know, if you do have questions throughout the event, there on the right-hand side, there is a pane for questions. So you can go ahead and enter your question into that pane. And then at the end, we're gonna do our best to get to all the questions we have according to time. If not, we will, of course, follow up with you after the event. So with that, I'm gonna hand it over to Ryan and he will take it away. Thank you.
Good morning, everyone. Hopefully everyone can hear me and see my screen okay. My name is Ryan Hewes, as Nick mentioned. I'm with Rysco Corrosion. Just a bit about myself. I've been with Rysco since 2019 and in the corrosion industry since 2007. Majority of my focus has been on cathodic protection. Also been involved in several AC interference studies over a number of years. One thing I am new at is delivering webinar presentations, so I apologize if I'm ahead of time if I'm too fast. So just a brief overview of Rysco as a company. For those of you who may not be familiar, Rysco was incorporated in 2007 at the request of a major Canadian oil and gas operator. Initially, Rysco was involved mainly in internal corrosion monitoring. A lot of the same personnel are responsible for all pipeline integrity things. This sort of expanded over the years into offering other services such as cathodic protection, failure analysis, and of course, the interference studies. As of today, the Rysco team has over 200 years of experience in the fields I mentioned earlier. We're based in Alberta, Canada, with agents in several overseas territories, such as North and South America, Middle East, Asia, and recently Nigeria. We've also recently expanded with the opening of an office in Aberdeen, Scotland. Currently hold several certifications, including ISO standards 9001, 14001, 45001, and these stretch across all of our group of companies. So this is basically just I guess a family tree, if you will, how the Rysco group of companies is laid out. The only thing missing from here would be our Rysco UK office, which would fall under the Rysco International umbrella. So I'll get into a couple of the challenges that I've seen doing these AC interference studies. The main one, I guess, in Alberta or the further north you go, is our unpredictable weather. A lot of you will know. We can range from minus 40 degrees Celsius to plus 40 throughout the year. Just adding to that, it's not uncommon to experience several weather changes throughout just the course of a day, which can cause some access issues due to mud and snow, etc. This is actually a picture we took this year of a study we did during the forest fires. You can see that was quite, the picture doesn't do it a lot of justice. It was quite windy as well. That's why his head's down so his hard hat doesn't blow off. You can see the snow can get quite deep.
Hey, Ryan, you're coming You're coming in a little muffled, I think, for a lot of us on the audio. Could you try and just be a bit closer to the mic, please?
Sure.
Thank you.
Is that a little better?
Yes, it is. Thank you.
Okay. So another major challenge we notice or see up here in Alberta, congested right-of-ways. Multiple pipelines can be owned by multiple different companies, sharing the same right-of-ways as the power line being studied at the time. Extensive fieldwork verification is required to determine what may change the values produced by the modeling later on. For an example, if a pipeline in the same right-of-way has its own AC interference mitigation in place, that should be known, as it would likely change the values you see. This picture here is just a shot of an area in northern Alberta, what it would look like typically. Maybe asked to look after one set of pipelines, which would look like that. You can see the challenge involved. So typically, the induced voltage levels we want to produce with the modeling should meet or exceed the actual values measured in the field. So if there are unknown factors causing influence, they need to be included in the modeling. As always, our goal is to limit the assumptions put into the modeling by collecting actual field data, and but still maintaining a degree of conservatism. So a third challenge, which is I guess a challenge for a lot of things, but just coordinating the field work. There are multiple parties involved in these things a lot of times. All the pre-planning you can do as for sites you're going to visit may not, a lot of changes can be made once you're at the field level. So it can be difficult to arrange. So I'm just going to get into one case study that we saw last year during an AC study. It involved a single transmission line, 138 kilovolt, with an average load of 84 amps, maximum load 628 amps, and a relatively short pipeline that sort of paralleled it, more across it, but so small. Not a lot of AC influence was expected. So the modeling suggested quite low AC pipe to soil potentials and possible step to touch potential values using these simple parameters. The AC pipe to soil potential values measured in the field were not much, but higher than the model was producing. So we were asking ourselves why, basically. So with our field work, it was determined that there was a secondary AC line shown here in yellow that also parallels the pipeline and provides additional influence that we didn't know about to begin with. With this added, we were able to verify the measures we noticed in the field with the modeling. Not only that, but the touch potential values exceeded our calculated thresholds for the fault occur. So we recommended the addition of a layer of crushed stone to increase those thresholds, mitigate the possible safety hazard. So some of the things that we include in our reporting of these AC interference studies, this is just kind of a brief rundown. There's quite a bit more information in the actual study, but We talk about the steady state results. We list them in chart and table formats. So these results are used to determine if the levels of induced AC could reach or exceed predetermined limits under normal operating or steady state conditions. And we would use this to determine if there is a need for mitigation. Also included in our reports are fault conditions results, also in table and chart formats. So these are used to determine if the levels of induced AC could reach or exceed predetermined limits should a fault occur. Most of this is based off of information received from the power line company as far as fault currents and whatnot, but also included our actual soil resistance and resistivity measurements. And again, we would use this to determine if any mitigation is required. So we also include in our reports modeled and calculated GPR or ground potential rise, step or touch potentials. We use this to determine if levels of AC could create a hazard to personnel at any point along the right of way or at pipeline appurtenances such as risers and well sites should a fault occur. And again, determine if any mitigation is required. So lastly, we look at everywhere where the pipeline and power line cross each other and measure distances in the field as well as on programs such as Google Earth, just to make sure that they're not within calculated separation distances where an arc could occur. Several factors go into this, such as particular fault current values at those towers, soil resistivity again, and structure grounding resistance. These are used to determine if the distance is past that safe separation distance, and determined if it is within that distance, what is needed to mitigate it. So that's all I've got here. Pass it over to Mr. Pikas. Take it from here.
Okay, and show screen. Is my screen being shown?
Yes, it is, Joe. Just need to move into presentation
Okay.
mode.
Yeah. Okay, just want to make sure. Thank you. Well, thank you, Ryan. And where I'm going to pick up, let me get past is in more highly densely populated areas like New Jersey. Okay, and you'll be seeing some picture New Jersey, one of the most densely populated states in the country. It is the most densely populated state in the country. So we went from Canada, being an open area, to some of the challenges that you would experience in New Jersey. This is just who I am. I started with Transco, or now it's Williams Transco, in 1966, and I've been going since. So let me go back. And I've been with Technical Toolboxes since 2012. So just to let you know, and here's some of the awards that I received over the years. Okay, I mentioned challenges. It doesn't make any difference if you're up in Canada, up in the wild. It doesn't make any difference if you're in the most densely populated state. I think this is going to jump on me, so be patient with me. We need to set the system to manual, and it's not. It's automatic. AC corrosion, has been a problem for more than 65 years. And how do I know? Well, back in 1964 to 68, the company I used to work for, Transco, ran a study with the American Gas Association on AC. It was a 4-year study, and I came into corrosion the year after they finished up the project. Well, they didn't finish it. We were still gathering data, pulling out coupons and things of this nature. Yes, we had coupons back in the late 60s. However, they were made. We made our own, and we actually they were pretty good sized coupons, and they were coated on the edges with a wet epoxy. And so kind of remember that because when we finally pulled them and looked at them, there was no corrosion on the bare areas. However, when we pulled the coupons, there was pinholes where we put the epoxy. Isn't that nice? And it was a eureka moment for all of us because we discovered that it was current density that was causing this. And this is why it was not recognized by the pipeline industry, AC corrosion. They would see it, they wouldn't see it, and they mistaken it for other causes. So you could understand the turmoil why things weren't recognized, but that report never went out really because it was a hand typed report. I still have it, by the way. I kept it because I knew this would be the future. My boss even told me that. He says, be prepared, Joe. He says, this is going to be the future. And boy, I'm still in it. So just to let you know, so that's how it started officially the industry. They have records of AC corrosion and problems back to the early 1900s. But of course that just fell through the cracks back in those days. I'm going to talk about high consequence areas versus the open country. Whether you're in an urban or suburban environment or a very rural environment, the same effects go on. The problem is when you're in an urban environment, everything is compounded. With your oil and gas coexisting, you're in people's backyards, which I'll show you, and you got everything and his brother out there, from fiber to what. So this is why I bring this up. So I wanted to give you the contrast of what Ryan showed earlier, even though it was smoky, a very big open right of way. Pipeline operators do not have the choices, where to install pipelines anymore because of the high concentration of people, and of course now the only thing that's open is any right of way that you could coexist with. So this is the key right there. So this is why we have a mix of electrical transmission lines and pipelines, because it makes good engineering and economic sense. Since somebody already has that right of way utility, under their belt. And this is what we're dealing with. This is kind of a smoky environment, but this is natural for these highly densely populated states. It's year round sometimes. So yes, that exists. We're going to be talking about these sources: unanticipated AC corrosion. We're going to discuss faults, Other utilities and interference, costly time and consuming calculations, because we need to get this done. There's not enough time sometimes. Product loss from failures, and then more costly after the fact problems. And this could be a problem. So you could see the issues that get compounded, and you need a model to handle multiple pipelines, multiple power lines, and that's the key. And this is what it's all about. So here's just a typical project that I was on about 20 some years ago. Electrical power lines. Here's your power lines. Here's multiple pipelines in this area, and our focus was on two of them, to be exact, a 30-inch and a 42-inch. The 30-inch was not impacted, and it was put in 1949. In fact, that pipeline and these power lines were commingled since 1949. But when the 42 come in and other power lines come in, the coatings changed. We went from a coal tar to an FBE, and that made a difference. And then all of a sudden, you got additional commingled systems in here, along with other pipelines. There was several other pipelines in here. So you do have some challenges when things happen, and you could see the distances between them and the power lines, and in some cases there's markers here too. You could see there's an oil line in here between the power lines. So just to let you know, there is a little bit of congestion. So what are our threats? We know we got global issues, with more heat, more cold, things of this nature. And so when you see the lightning, right now, the Houston area where I live is we're on our third week of 100-degree temperatures in that range, and the weather weatherman says, well, he says you could expect another week of it, and maybe more prolonged type of temperatures with the increase in temp of warm up in the future. So that doesn't look good for us. So air conditioners are running all the time. AC loads are at their max, and what do we always try to look at is peak. So which one do we use now? Do we use the max? Do we use the peak? We can't use the defaults anymore because of the issues of loads on AC loads now, and their duration, their length that they're operating. So because of all of this, we're seeing more storms that are being created and things of that nature. So we're getting more faults and things of this nature. So there is a lot of energy transferred, and the problem is you could get not only damage to the coating, but damage to the pipe also, depending on your proximity to the towers. So these fault conditions may only last short periods. And what do we mean by short periods? Microseconds to milliseconds. So depending on what whether it was a fault or a short to wires touching each other, from the winds, we'll make that determination of length of these short periods. So keep that in mind, what we're dealing with. I mentioned the ability to do multiple pipes and multiple towers. Someone asked us the question, hey guys, what is your maximum? So all we could do is, all we could just tell them is one of our clients have put in 31 power lines. And we know a client that put in 24 pipelines. Can you go more or less? Well, we know it could go less, but these are the real things that have occurred that we know of. Can we go more? I'm sure we could, but is it necessary? This one client wanted to test it out, and it worked, so he was happy, and so were we to get that kind of feedback. We've been using the PRCI model. That engine has not changed. However, we've made additions to that engine. And what are these additions? Well, in our development and enhancements, we made it to be more easily understood, the model itself, and easier to mitigate AC induced integrity problems. That has changed the dynamics of the program, not the engine or anything like that. That still remains the same from the original research, but the ease of operation and modeling. And I wanted to bring that out. And as you could see, we got 1, 2, 3, 4 pipes with the current densities and then the induced currents that follow. And they're all color coded and so on and so forth. So this is one of the benefits of the program. Yes, we could go up to these type of that number of pipes and power lines. This is what I'm talking about. Working in people's backyards. When you work in a place like New Jersey, I worked there for about 17, 18 years. One of the things that you deal with is congestion. And as you could see, here's these power lines. Here's the houses behind, adjacent to the right-of-ways. So you're literally working in people's backyards, in their gardens, in their driveways, and things of this nature. And everything has to be marked out, including where you're going to excavate, where you're going to put your mitigation cable, and things of this nature. So it's very, they have a lot of regulations there, which is good because of what you're dealing with, this type of congestion. And then you got fiber here and other types of communications. So once you get the information, that's gathered from the field, you could literally start loading your system in minutes, not hours, to mitigate these voltages and faults. And this is one of the things I want to point out. Most of your work will be in the field, as Ryan indicated. His challenges were weather and things of this nature. Here you have challenges just trying to work through all these properties and things of this nature. So no matter where you're located, you're going to have different challenges. So ACPT has multiple options to mitigate based on, and here's the key, buildability of the grounding and anodes, because this is what it's all about. When you're using ArcGIS and when you're using Google Earth and when you're using mapping systems like this is where you begin. This is where the capabilities come in, where you could see what you're building and not just modeling something that says go put something in for 10 miles and any way you want. You could control the build ability because you're dealing with situations like this using your mapping systems. And here's an example of where we create sections. We tie all of towers to get in there simply for the fact that when they're all geo-referenced, we could run faults on all of them. And that makes a difference because the regulators also look at this. Hey, do you guys know what your fault conditions on your system is for every tower? I.e., you could do this. You could get those this information very quickly by just drawing a section line. And how long does that take? 10, 15 minutes, depending on the length of the line you're doing. Say a 10 to 15 mile line shouldn't take you more than 10 or 15 minutes. Minute a mile. That's what I say. So AC current density, a lot of folks are using the NACE criterion. The Barnes layer, you could follows the NACE guidelines. If you want to use a different system, fine. If you're doing curve fitting or anything like that, the program handles it. We're not going to argue if you use the Schlumberger method, the NACE method, or some other method. It's your choice. But as long as you're using a layered system that you could account for, for the different calculations, the modeling. Single and combined graphics, that's your choice. We have import, export, updating of data, ease of use, most project in hours, not days. And then most of our training is less than 2 hours. We had people that said, don't even bother. I understand what you're talking about, Joe. I don't need the training. And then we've had people, just walk away and do it all on their own. Most people, it's 2 hours or so, plus or minus a few minutes this way or that way. But this is what we're talking about, ease of use. We're not just talking about AC. We're talking about a whole pipeline system like this. Whether we're doing HDD, whether we're doing road crossings, whether we're doing an R-string calculation. This is what we call our hub environment. And so everything should be tied together or integrated together, whether you're doing blasting calculations, whatever it may be. This is the nice thing is when you can combine, and one of the things we have is our R-string calculation tied to every piece of pipe in here, in our hub. So whatever calculation you're doing, you could account for metal loss. The programs are set up where that R-string dig site will come up to show you, yes, I got a certain amount of metal loss. Do I want to consider it? You could check the box. You have the choice to pick that location, check the box, and it'll calculate your remaining strength as well as your stresses and things of that nature for any of these calculations in here. So this is one of the things that we have. So we don't end at, well, the data is in some disparate area. It's all integrated. So anytime anyone else in your organization is running a calculation, they could bring up that information very quickly. And if there's AC metal loss in there, and it's been picked up by the PIG or inline inspection, it can be handled very quickly. So you don't have to run from one group to another. It can all be brought together in one system to meet the new mega rule requirements of digitization and mapping. Okay, so also we know the challenges that are pipeline engineers are facing, and our solutions, some of our solutions that we're looking at is knowledge transfer through our training, product learning library. Take a look at our sites, and then our wiki site too, with all the information. And then also we're having all of our applications where all you have to do is just hit the little question mark, and it'll take you to the calculations. So we even brought that to the front door too, instead of coming in the back door. So these are the kind of changes we've made. Knowledge solutions. This is the goal, is to share our knowledge and that of other experts in the industry. our mitigation software. Let me go back here. It's to help even the power line operators. You know, the whole key is we don't work in separate stovepipes anymore. We work together as teams. And when I say teams, right across the organizations, all organizations, you know, and that's one of the things we have in our toolbox that we have a collaborative feature in all of our applications that you could share all your data or part of your data to any part of your organization. So you're no longer sitting down, you know, in a separate office anymore. You're actually, everybody's seeing what you want them to see, or vice versa, or everybody. You know, depends how you're set up. And that's they can't change your data, and that's one of the nice things about it. So we're connected to engineering standards, other tools, you know, in the pipeline cycle. You know, the maps bring it all together in a geospatial. I'm a visual person. You know, we're talking about visual reconnaissance, existing databases, leveraging, and disparate GIS systems. We bring it all together. This is what it's about. This is the way it was supposed to look even back in the mid 90s. And it never took off. You know, GIS systems never took off the way they were supposed to. That brings me to a poll question. I think we finished up a little bit early on this one. Would you like more information from Rysco around their modeling techniques for AC mitigation? Would you like more information from technical toolboxes regarding the AC mitigation power tool, both or neither? I think we have, is that question sent out?
Yes, it is, Joe. We'll give it just about 10 more seconds and then start diving into Q&A. In line with that, so with Q&A, I've seen we have a couple questions coming in so far. If you do have questions on kind of how Rysco does modeling in Canada, or on the AC mitigation power tool that Technical Toolboxes has, please start filling your questions in on the right-hand side. Looks like we've got about 5 or 6 now. So after this poll, we will start chipping away at those. Joe, the first one individual is looking for more information on what the Barnes layer is, and can you talk about the context there?
Oh, okay. Yeah, the Barnes layer. This has been around for many years, and the purpose of the Barnes layer, or any set of layer data. Oh, what happened here? Did we get kicked out? Here we go. Yeah, any layer data is the modeling for AC mitigation is based on different layers, like for the induced voltages and the fault voltages is based on the deep layer. Okay, and somebody says, well, what's the deep layer, Joe? Okay, well, the deep layer could be 30 meters or 100 feet. Okay, it could be a little bit greater than that. But it has to be at least a minimum of some distance, and I think the consensus in the industry now is 30 meters. Then we have another layer that is for what we call, there's a couple layers. They got different names. It could be called the corrosion layer or the current density. Okay, that's where the pipe layer is. Okay. And of course, and the question is well, my layers vary. I mean, my pipe depths vary because I cross. I have HDD crossings. Well, then you would use the appropriate layer for you know, for that crossing. You know, whatever it is. You know, whether it's 10 meters or about 35 feet or something like that. So you have that, and then you have your what we call the conductive layer, and that would be your soil surface. Where if there was a conductive fault. So this is the reason why the modeling is set up on layers, and how you determine those layers is up to you. There's many ways. There's pros and cons to each one, but if most of them will give you something, but the most common one is the Nace-Barnes layer because of its ability to cross long distances. Thank you.
Thanks, Joe. The next one might be for Joe and Ryan. The question is, what equipment is needed to obtain soil resistivity at a 100-foot layer?
Want me to take that, Joe?
Yeah, you could handle that one. Yeah.
Yeah, it's just the typical equipment with longer leads, the typical soil resistance meter, which is then used to calculate the resistivity. I don't know if you have anything to add to that, Joe, or not.
Yeah, yes, I do. When you're doing deeper depths, such as 100 feet or greater, or 30 meters or greater, make sure that the voltage on the meter is high enough. And there are certain meters out there that I'm not going to mention names, but you have what we call the cathodic protection soil resistivity meter that's usually limited to about 6 meters in depth. Why? Because you're just putting an anode bed in. Okay. When you're dealing with AC mitigation, you should be thinking in terms of at least 30 meters or at least 30 meters. To get a good assessment of that, those depths, because you're going through different layers of soil. So make sure your meters have the capability to go those, for those deeper depths. I caution you on that. So there's really two types that are out there. One for your conventional ground beds, and then there's the others, for going for deep areas. Okay.
Very good. Thanks, Joe. Next question. What loading do you recommend for assessing the inductive steady state voltage?
It depends on the resistivities. Let me answer this question, and you could follow up, Brian. So I'm going to take a case where a half a volt in a brackish water area caused AC corrosion. Okay, a half a volt. Okay. Conversely, if you're in a higher resistivity environment, obviously it's going to, the voltages are going to be higher. There are graphs out there and tables that could help. I have in my user guide that could help you discern where to start looking for the issues. So it's really contingent upon resistivity and the various layers that you're dealing with. So keep that in mind. So it could be a half a volt up to whatever, up to 10 volts or greater. They use 15 volts for safety. That's a caution. And why is that? Because if you have a riser or a valve or anything like that, there are rules now and regs that, in fact, it was the Canadians who started that rulemaking. It used to be 30 volts, were set, and the Canadians, what their rulemaking, it was adopted by the U.S. that 15 volts would be the safety factor for humans, and then that's when you're doing your touch potentials. You know, you should be thinking about those, about putting separate mitigation, you know, around your risers and things of that nature, like your grids and stuff like that to ground those areas, you know, for personnel protection.
Okay. Next question, I think, is a follow-up to the question 2 questions ago around the equipment. There's a question on, you know, what is the voltage capability on the soil resistivity instrument that's generally needed for those deeper measurements, like at 100 feet, 30 meters? Any comment? Good.
Go ahead.
Sorry, I was jumping in to get you. I didn't know if that was one that you all wanted to take, or we can move on to one of the others.
Oh, yeah. Did you get that, Ryan? Did you want to answer that one?
Yeah, I'm not really sure I understand. So what voltage ability?
They generally go pretty high, and what I mean by high is well over 100 volts or higher. Let me give you an example. When I was involved in corrosion and we ran into situations like that years ago, I'm talking about, you know, 40, 50 years ago, we actually used generators to you know, to get the right resistivities, you know, to build up and take readings. Today, it's compacted. I don't know what the exact voltages are. You could look them up. Go to any one of your folks that sell this equipment, and they could give you the specific voltages. I don't have the specs in front of me, you know, what the voltages are. But I know one thing. It'll make those earthworms jump out of the ground.
Very good. Thanks, Joe. Okay. I guess let's see. Next question. What types of mitigation does the AC power tool have?
It has 3 types. One is what we call discrete anodes. Okay. And a discrete would be something like a deep well or something deep. We also, if your companies allow it, and you could also use that same system where we have for discrete for putting a if you have an isolating flange. And if you put a decoupler across it and it goes to a station, such as a compressor station, a pump station, to ground, you could use the discrete anode portion of that or a casing by just putting a decoupler across that, and that'll act as discrete because it's typically in one area. So keep that in mind, that you have that option in there. A lot of folks don't realize that. You know, as long as that case, if the casing is electrically isolated or electrically effective, if it's shorted, that's good because it's a drain point. It's already draining AC. Then we have distributed. So if you want to put your anodes on a 30-meter basis or a 15 or 10-meter basis, you take the resistance of a single anode and just apply it to whatever how you want to distribute it in that section. And then we got wire replacement. And we say wire replacement because it could be zinc or copper, or it could be something like the mitigator. I hate to use the, you know, a commercialization. And and that's okay because all of our calculations are based on resistance. We're not basing it on a specific anode. So if you have a resistance to ground like you were calculating, that's what everything is based on. So it makes no difference what type of anode system it is. It's the resistance to ground calculation that counts. So whether it's say 100 millimeters thick, or 3 or 4 inches, or even 12 and a half millimeters, or half an inch or so. It doesn't make any difference because all our calculations are based on resistance to ground. And you could use them. You can mix and match. And this is the nice thing about it. Remember I said that we use the word buildability. This is one of the keys to the program is that you can mix and match based on the conditions that are out there. So if you had to use all 3 methods to mitigate, you could do that. So I just want to point that out. I'm not saying it's common, but you have that capability to do that.
Okay, thanks, Joe. Looks like we've got time for 1 or 2 more. I guess moving on, I guess another question on the AC Power Tool. Can the AC Power Tool calculate all faults for each tower along the right-of-way?
Absolutely. This is a question that has come up many times by the pipeline operators here in the U.S. I don't know about Canada, but one of the questions they've been asking, during their audits is, hey guys, do you know your fault threats for every tower that's paralleling your pipeline? And of course, the pipeline operators are like, are you kidding me? No, we don't know. Well, you have, even if you don't have a AC per se problem, you're not worried about AC corrosion. Maybe it's just, the resistances are too high or whatever, but you always have you could have a threat to a fault. And how do you know it's going to happen? Well, this program will allow you to make those determinations, those assessments. And this is the nice thing about something like this is that if you wanted to track every one of those towers based on different load factors or whatever you're dealing with, or different changes from year to year, you have that ability to do that. So keep that in mind. So just from a regulatory standpoint, to determine your threat fault threats on the pipeline, you have that ability to make those calculations very easily. That's a great question.
Okay, last question. During fault conditions, does the AC Power Tool differentiate between conductive and inductive faults?
Absolutely. One of the things, let me go back here. I think, where was it? Well, I had it here. Oh, it's not on here. May not be on here. Okay. One of the things we have here is, let me go back here. Is for faults, we have the capability to, I don't see this graph. What happened to it? Anyway, we have a checkbox, and the checkbox will allow you to check for conductive faults or not. So you have you have that capability to yeah, I don't see it here. You got AC modeling. Where did it go? It was in my other deal here, but anyway, it must have got lost. But anyway, you do have the capability to do that. Put the checkbox in there, check it or uncheck it. We always default it to you know, for both inductive and conductive faults. So we think it's that important. And so this is one of the things we were concerned about, particularly in light of the regulators asking those type of questions.
Very good. Well, thank you again, Joe and Ryan. And thanks you all for your attendance and your good questions. And you will get the recording from this event within the next 48 hours, and we will follow up from there. So thank you again, everyone. Have a good day.
Okay, thank you. Thank you, everybody. Good questions.